Hello and welcome to the Learn Along series. We are doing NLP with deep learning. This is stream number 10. Uh, Today we'll be reviewing lectures 5 through 8 in the video series, links in the description. First of all, I would like to wish you all a very happy new year. If your new year resolution is to learn deep learning or just around technical skills for the future, like uh, NLP and computer vision and stuff like those, um, tag along, because I would be doing a few of those and would definitely be acting as your accountability partner, because my motivation is to just keep on doing these one every day. Before we proceed, I'd quickly first check my sound. Give me 1 second if everything is okay. Anybody in the chat, if you would also let me know if my mic is not working properly, but give me 1 second. Okay, uh, I think everything looks fine. Let's not waste time and jump into our course material. So we're not watching any lectures, we're just quickly uh, sort of running through the slides. So I'll just change this. Yep. Okay. I think you guys can see. I can zoom in a little bit more. So we reviewed lectures 1 through 4 a few days back. Now let's start with lecture number 5. I think this was this linguistics, structure, dependency, parsing. The idea is to just go through these. We're not going in detail. If you want to go in details, obviously watch the lectures, because these are I mean, for me these are difficult, and because they are completely new out of my zone. So do watch the videos if you're trying to understand in detail, but also just grab a pen and your notebooks if you're trying to also jot down important concepts or formulas along with uh, me. I already have my notes open, so I'll be just also looking through these um, to see if I have everything, or if I have to improve on my notes a little bit. But I guess you guys can see, or I'll just do this slide mode. Yep. So dependency parsing, I think the idea was, this is more about a linguistics class than anything else, because the concept was to learn, I mean, how English as a language, for example, works, and how other languages would have different ways of representing phrases and words and sentences and stuff like those. Just 1 second. Okay. So 2 ways of linguistic structure, constituency. Oh yeah, so they're representing what's the determinant, noun, adjective, and then preposition, noun. What are the structure types? I mean, I didn't feel that this is so important to uh, learn the exact. I mean, it is important to learn the exact phrase, of exact representation way, but not too specific in what exactly is happening. I mean, for example, here this is a good sort of a statement which is breaking down all of these individual phrases of. So the board approved, and now you're basically asking questions of what it approved. It approved an acquisition, uh, and then the defining part of acquisition is that there is of Royal Trust Co. Now this is based in Toronto. The price was $27 a share, and when. So it's basically asking these questions around what they did, who was involved, where they are located, what price, when, like these kind of questions. So you're trying to basically um, create a sense of attachments to what is happening in the particular statement. A little about ambiguity. Obviously, English is ambiguous, but becomes even more so when we have like phrases and not exactly sentences. For example, doctor, no heart, cognitive issues. Now, no heart and no cognitive issues, or no heart, cognitive issues. I mean, similar, some funny examples. Uh, so his first hand job experience, uh, obviously double meaning. Uh, this is another good one when there are no like commas or sentence separators. It's just like one big phrase. Mutilated body washes up on Rio Beach. Now, here is where the point of contention becomes to be used for Olympics beach volleyball. Now, mutilated body washes up on Rio Beach. The beach that would be used for Olympics beach volleyball, or the mutilated body would be used for Olympics beach volleyball. So, uh, I mean, we understand what it should be, but still there is ambiguity for somebody who's, let's say, who doesn't know how to properly read English, or if, for example, the machine, they're reading English for the first time, they can interpret both um, with equal likelihood. Now, this was, I think, way of representation. You're basically dependencies. They're basically dependencies, and then you're trying to building this tree of what that is and where it lands based upon what's happening. Uh, so yeah, I mean, it's a statement. Now the problem is, if we try to backtrack what the exact statement was from here, I think it's a little difficult. Uh, this representation in itself makes sense, but the fact that you have to, uh, for us to understand what exactly was going on, once we, I think, if this was the starting point, this feels a little difficult. I think there was another method that'll be the, yeah, it's a little bit about history. Uh, yeah, so I think this was a different methodology where you have the statement and then the arrows are created on top of that. I think we'll have a few later on. Yeah, and this is start, but I'm jumping to a better example that was there later on. Yeah, I think this is one of it. I'll give a talk tomorrow on bootstrapping. Now, a sentence is parsed by choosing for each word what other word is a dependent of. Usually some constraints. One word is dependent of root. We don't want cycles, correct? This makes dependency tree. Final issues where the arrows can cross, non-projective or not. Okay. So let's say the word is, I mean, give is the root word. Now, give what? So a talk. One arrow goes there. Then obviously the prepositions of I will, and then also give like tomorrow. So when. So there's another arrow. I'll use my mouse. I think you guys can see. Yep. So you have these arrows basically explaining the root word of what is happening, when it's happening, who's doing it, all that stuff. Then the other term is bootstrapping, and bootstrapping also has a preposition in front of it. So basically, yeah. Oh no, not this one. Yeah, they're obviously different ways to do that stuff. uh, and I think this was the basic transition base. So we're basically shifting. I think we'll better example. Yeah. So we start with just the root, uh, and then we're basically giving one word each, and then I mean that's the methodology of you keep on shifting. Uh, then you look at the left arc and then the right arc, and move to include every other word or every next word actually, uh, to create this transition. I mean, it's just the fact that it's a methodology that the machine would use to keep on uh, parse the entire statement. Let me see if I have anything else in my notes. Oh yeah, okay, that's it. But yeah, I mean, nothing, to be honest, nothing really to memorize here. It's just mostly one of the ways or one of the concepts uh, we or just know what happens in the background when we are parsing uh, a particular statement. Give me 1 second. Yeah, okay. Uh, so we'll keep moving. Uh, yeah, I mean, this is just an evaluation metric. Again, I'll just keep on skipping something that I feel is more just conceptual. I think CNM was one of the professors parser that they built, which not only had like better accuracies than most, it also had a great speed, sentence per second. Uh, Now there are even better ones out there in the market, uh, so you don't have to really worry about going through each and every of those. Uh, yeah, talking about their paper. Yeah, okay. I think that was the last slide. I mean, in summary, I'll just say dependency parsing. We are basically trying to find dependencies to all of the root words within a statement, and there are different methodologies. But obviously, I would say none of the ones that I just mentioned here. I believe there should be more in. Oh, I'll just quickly go through the notes first if there's anything. But there's just to understand what's going on in the background. If you're too keen, obviously, uh, watch the lecture in detail. But I would just say this is just for an understanding point of view of, as I said, what's going on in the background. Oh yeah, this is the paper Chen Manning that he was mentioning. Everything is there uh, in the description. So if you want to just uh, read through these in your time. Now, just the fact that this is, giving you just an overall understanding, but it's from like 2009, and things have changed so much that even if this concept is relevant, I would say this is not the new age method or like the vanilla method as they call it for today. So uh, I'm not. I'm just looking for if there's something different uh, and also easy to go through. I'm not reading any of these papers. Universal Dependencies website. I think, yeah, this is this a repository of all languages? Oh, looks like it. Let's go to English. Let's see what's going on there. Wait, what happened? English. Oh, so there are different tree banks. So this is where I think you can download the entire corpus. Okay, I mean, good to know. Obviously, I'm not doing it. Yeah, I'm rushing through getting more into RNNs and attention. I mean, I feel the last couple of lectures were a lot more important. So I'll basically skim through the first ones and then spend more time on, I mean, now starting RNN. Yeah, why do I have regularization here? Okay. Finish a few things we didn't get to. Oh, this is for the, okay, last lecture. I think these were a few, I shouldn't say tips and tricks, but a few concepts you need to keep in mind in order to have a better model training, as well as just in general a better performance of your neural networks. One was about regularization, that is in order to prevent overfitting. Read about L2 regularization if you're interested. Other than that, I think dropout was to remove a few nodes so that we can create our neural network a little more time efficient. But yeah, test time half the model weights, not twice as many. This prevents feature co-adaptation. Yeah, okay, I don't know what that is. Not sure if this was also discussed in class, because I don't have this here, but okay. Vectorization, looping over word vectors versus concatenating them all into one large matrix, and then multiplying the softmax weights of the matrix. So the first one took a lot more time than the next one. So it's basically we want to concatenate them all into one large matrix and then multiplying the softmax weights with that matrix rather than going to individual one hot vectors. Okay, I mean, good to know. Yeah, 10 times faster. Great. Nonlinearities, I think we already discussed these. So not sure why they're here again. Now it's all ReLU, so start with ReLU. Initialization, yeah, this was a Javier initialization, which is, I mean, I shouldn't say the standard, but this is the only example that the professor gave. And this is like the variance is 2 by the size of previous layer, size of next layer. Optimizers, yeah, also there are different optimizers. Mostly the professor has just mentioned about stochastic gradient descent, SGD is that, but also mentioned Adam is another one, and these have like different learning rates. Some have cyclical, some have based upon wherever you are in the model training, so it has a dynamic learning rate. So Adam is one example. I mean, there are other names mentioned here, so keep in mind, obviously there are many things to do stuff and they would have different performances, but in order to just get started, just stick with one and then you can keep on tweaking later on. Yeah, learning rates. So as I was saying, there are fancier methods like cyclical learning rates. I think this is like an exponential, yeah, decrease with every epoch increasing. So okay, that was what I learned. So this is where is the core of our this lecture. Give me 1 second. Increasing. So okay, that was what I learned. So this was where. Okay, language modeling is the task of predicting what word comes next. So if we have a phrase like the students opened their, now we are trying to predict the next word. There are obviously different words, these would have different probabilities. So more importantly, we are trying to calculate the probability of the next word given the previous words. And if a system does that, it's called a language model. What happened here? Oh, yeah, sorry about that. You can also think of a language model as a system that assigns probability to a piece of text. So uh, you basically have, this is like for all of these words, the probability of that word, I mean obviously it's not a good example, the probability of that word given the previous words. So we just basically go all the way back to the first word. And this is obviously a product. When we use this every time, we have Google autocomplete. When we are even texting, we have these best probability of words that you would most likely use. Yep, autocomplete. N-gram language models. So I think this is like instead of one word, we'll use a chunk of n words. So the idea is to collect statistics about how frequent different n-grams are and use to predict these next words. For example, if there's a 4-gram, and in our corpus we look for all the students open their 4-gram, and if this appears multiple times with like the next word books, then the probability of books is a lot higher. That should succeed this 4-gram. We make a Markov assumption. xt1 depends only on the preceding n minus 1 words. Probability of n-gram, probability of n minus 1 gram. Oh yeah, so it's the conditional probability. Basically, so if it's a 4-gram, we are trying to figure, I'll show you with this example. If there's a 4-gram, basically students open their books, if we are also including the other word, and then we're finding the probability of that phrase by given students open there. So we've like shifted to the next word. So yeah, it's just basically counting how many times the word has appeared in our corpus. Okay, yeah, I mean this exactly is the example. We are discarding everything else because we are just looking for a 4-gram model. So 4 words, students open there, and then the word, and find like probability of all the occurrences. So books, exams, so on and so forth. Now you obviously see the problem with this. We no longer have the context. So yeah, sparsity problem is sparsity problem is like we will have very less. The higher the number or the higher the n, basically we will have very less of those phrases occurring. So we will have, I mean, the less the number, the worse your model becomes. So we have this sparsity problem, because if we decrease the n, we may not get a whole lot of context, but if we increase the n, we will have very less of those phrases occurring. I mean, yeah, I mean, this another problem. we keep on increasing the n, we would have a much larger corpus, because we are just creating all of these n gram chunks. In practice, I mean, I don't see this as like the new age method in practice anyway, but I think this was one of the examples. Was surprisingly a grammatical. This is all n-gram generated text, but incoherent, because obviously it lacks context. If it's looking at like these three phrases, it's missing out on today, it's missing out on price, maybe. So not a whole lot coherent. Plus, I think it also treats like commas as words, so that's why you see commas appearing like this weird space comma, and same for I think full stop. You have a space here. Okay, how to build a neural language model. I mean, I think this is similar to named entity recognition. You have these 5 words, and then I mean what we're basically trying to do is we create one hot vectors for each individual word, and we are concatenating into one. Then we apply our WE plus P1, basically our hidden layer transformation, and then we apply the softmax to show us what the winners are. So books and laptops are the winners here, for example. So yeah, this improves the sparsity problem, and we don't need to store or observe diagrams, but obviously the window is too small. Enlarging window enlarges W. Okay, window can never be large enough. Agreed. X1 and X2 are multiplied by completely different weights in W. No symmetry in how these input process. Okay, we need a neural architecture that can process any length input. Okay, I mean conceptually this makes sense. So here comes RNN. I don't know how well we are doing on time, but I think we are here on the most important concept here. But so the idea is that there's the input sequence, and then the hidden state is appearing one after the other, basically on a recurrent basis. So you would have the same hidden state weights that keep on appearing, or that keep on solving for the output weight. So the core idea is apply the same weights W repeatedly. It says here in the top. I mean, we're doing a whole lot of the same thing. It's like the same structure, creating one hot vectors, embeddings, but the fact that we are creating these hidden states which have the same weight that passes through, and then the last word, or whatever the last word or phrase, word in the phrase, that determines, or that gives us the output on which we are applying the softmax functions to find. So now we are not just looking at like one word or like one hidden state. We are looking at all these individual ones, so that we have a little bit better context of what exactly is happening. This input sequence could be much longer. Yeah, that's the point. Like, we are trying to build a big RNN, or because we can use the idea from language model, like the n-gram version, was that we need an architecture, neural architecture that can process any length input. So we are basically getting more length. Exactly, can process any length input. Model size does not increase for longer input, same weights applied, so there is symmetry in how inputs are processed. This is slow, difficult to access information many steps back. I think we'll learn on this later. Yeah, I just look at my notes if I have anything else. Yeah, okay. Get a big corpus of text, feed into the RNN language model, compute y hat, predict probability distribution of every word, give word so far. So the loss function is the same cross entropy. Uh, we discussed this in the last one. I mean, this was in lectures 1 through 4, but we discussed it in the review session as well. The predicted probability and the true next word. So we're trying to find the distance between the two, and the cross entropy, and you average that to get the overall loss for the entire training set. So you do that for every y hat. So basically a summation across all y hats, and then you're trying to find the overall loss. Yeah. Oh yeah, same thing. So we calculate the loss, and then you just do the average of these. Teacher forcing. I mean, in practice, instead of doing the entire, batch, we'll obviously use stochastic gradient descent. So basically, use uh, uh, use chunks so as to make this more efficient. Back propagation for RNNs, I think it's the same. Let's skip through a better slide. Yeah, we know multivariate. It's the same deal. Oh yeah. So we talked about back propagation. We are passing our gradients back through our model. Was there any equation here? Backpropagating over time steps, summing gradients as you go. This algorithm is called backpropagation through time. So we're basically summing all of these steps. Wasn't there any? I think there wasn't. Okay, I know there was a little bit. So del J by del W would basically be a chain rule of, applying chain rule. Del J by del W over I multiplied by, there is I here, which is not the denominator. So there's going to be del WHI by del WH, which is like obviously the denominator here. But that is going to be 1. Basically, there's just a sum of all individual WHs, which is the same. So it's all 1, which is why I think the other term is not here, and this makes it a little bit confusing. Okay, generating text with RNN. Sample output is next steps input. Yep. Let's have some fun. I think these are RNN trained. I'll skip through these. You can see this look. This is all RNN generated, so this looks a lot like an actual test. I don't know, however, if it's coherent or not, but this looks a lot like that. So yeah. Evaluation. So the evaluation metric for RNNs is perplexity. This is how you calculate that. Just keep that in mind. We're basically trying to minimize perplexity. So lower perplexity. I don't know why I can't say this, but lower perplexity is better. RNNs have greatly improved perplexity. Yeah, okay. What should we care about language model? this is involved in a lot of stuff. Predictive typing, I mean, we do that every day. Speech recognition, it's basically Alexas and all Google Minis of the world. What I am a lot interested about is machine translation, summarization. Uh, so there are obviously many applications. System that predicts the next word. RNNs take sequential inputs of any length, apply the same weights on each step, can optionally produce output on each step. The thing about optionality is, I mean, we don't really need that unless I think we just try to calculate the loss, or we want to see what's happening intermediate. We basically want to see like the final output. That's why you see the word optional here. But RNN is just one way to build language model, but that's not all they're used for. They're useful for much more. For example, part of speech tagging. If it's a noun, it's a verb, whatever that is. Sentiment classification, another interesting application in general. Uh, how to compute sentence encoding, take element-wise max, a mean of all hidden states. Okay. Encounter module. Oh yeah, okay. Speech recognition. I mean, you're just sifting through whatever new or whatever RNN applications are out there. Terminology, GRU, LSTM, yeah, we'll get to that. Just vanilla RNNs are what we just saw because there are more fancy RNNs in this world. I think that's it for this lecture. But let's just look at suggested readings if there's anything. Okay, yeah, these are just the notes. N-gram language models, I think there's the book by Girafsky, so there's additional reading for you if you want. Andre Kapati, okay, unreasonable effectiveness or RNN. Yeah, I think this looks like something we can read, but yeah, not right now. Nope. I don't know if you guys are readers, have read Noam Chomsky, but controversially he has been one of the very popular linguists out there, so maybe something to read on that, but yeah, I'm not getting into this right now. I'll get into vanishing gradients. We can take a quick break. We've been going on for 45 minutes. How about that? Let's take a quick break, 2 minutes or 3, and let's get back on vanishing gradients. Okay, we are back. Let's get right into vanishing gradients. Yeah. Okay. So the vanishing gradient problem is basically the further along we move in our RNN layer, the lesser we hold on to the context of what happened earlier on. So it's basically, from a gradient perspective, we keep on our gradients keep on decreasing or just vanishing the further away we go from a said word. So that constitutes a problem because we're no longer holding on to the context that we wish to. So yeah, sorry about that. So that's why they are now more fancier RNNs, LSTM and GRU, for example. Oh yeah, I mean, it's already explaining. So think from a gradient perspective. If we are back propagating, trying to pass back the gradients, so if we're trying to compute del J4 by del H1, we're basically applying the chain rule. Now, if these are small, the product is obviously going to be really small, so it's just vanishing. Yeah, I mean, it's just the same thing, trying to explain more mathematically. Yeah, I just skip through these. Why is vanishing gradient a problem? Gradient signal from far away is lost because it's much smaller than the gradient signal from close by. So model weights are updated only with respect to near effects and not long-term effects. There's no example here, but like if you remember earlier on, there was an example in which the word proctor was like the first word of the statement, and we were trying to look for something very further along in the statement. If we no longer have the gradient for that word, we basically have lost the context of who is asking for what. So I think there was something related to Proctor was asking the students to open books or something like that, and books was like the word to be predicted. Now you're asking students to do something, but if the word Proctor is not appearing or the gradient of the word is too low, you have lost the context around, I mean, maybe the exams. I mean, the correct word would have been exams because of the proctor, but if not of that word, the probability of, let's say, books would be higher than that. So I think that's the difference, or that's the problem that vanishing gradient constitutes for. Quickly look at my notes if I have anything. Yep, okay. If WH is small, then obviously because of the product it goes very too small. Another explanation, gradient can be viewed as a measure of the effect of the past on the future. Yep, okay, I think that's what I was also trying to explain. If the gradient becomes vanishingly small over long distances, then we can't tell whether there's no dependency or if we have the wrong parameters to capture the true dependency. Okay, I think this is another example. Better to look at this one rather than visualizing the other one. It's a big statement. When she tried to print her tickets, she found that the printer was out of toner. Now the tickets is appearing here. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her what? Now we know it should be, the target word is tickets, but because this word is appearing way back into our statement, we probably would have just lost the gradient, and this is more dependent on the recent words. She finally printed her. Now I don't know what the higher probability for printing for this context would become, but you get the point of the fact that tickets is right here at the back. We're not even sure if this will give us the correct context or hold on to that information. Yeah, if the gradient is small, the model can't learn this dependency. The model is unable to predict similar long distance dependencies at test time. Yeah. Syntactic recency, sequential recency. Oh, okay. The right of the books is our. Oh, yeah, that's another thing. Now, this is a grammatical issue. Because of the word books, and it's like the last word, the preposition are gets a better weight because books are whatever a statement could be, but the actual context is for the word. I mean, the real subject is the writer. So is the correct one, which is the syntactic error we are holding on to the actual context of this phrase or the statement. But because of sequential recency, books may dominate, or they will have a bias towards the recent word, and R becomes a higher probability preposition. So just a little more idea around vanishing gradients. I think on the other side, exploding gradient is also a problem because you may go way too far in your SGD update steps. So think of a simple, we're just trying to minimize, and we, instead of smaller steps, we just go way too far and maybe even outside our local minima territory. So both is a problem. Yeah, gradient clipping, I think just a solution for exploding gradient. We are basically normalizing that, scaling it down. Another thing to note, especially when you are on like cliffs and stuff. I'll move here. How about RNN separate memory? Okay, LSTM. This is where this is all leading to, trying to have like a concept of like memory in RNNs. Okay, so I think this is a heavy slide, but there are different gates that we define: forget gate, input gate, output gate. The idea is basically, okay, so control gate, forget gate is a control gate for what is kept versus forgotten from the previous cell state. Input gate is what controls what parts of the new cell content are written to the cell, and output is obviously controls what part of the cell are output to the hidden cell. So we basically define these three gates, and then this creates our new states. Or so new cell content is whatever needs to be written to the cell. You can see this. Is this a oh no, sorry, cell state, which basically will erase some content, which is the forget, and write some new content, which is the input. So we are dynamically updating our inputs as well as we go along forward. So you can see this is a function of both FT, the forget gate, and IT, the input gate. Cell content, yeah, this is the like new cell content, so that's what we've defined here. CT minus 1 is the previous cell content. So this is the cell state is a function of these four entities, and a hidden state, which is the output, would basically read some content from the cell. So this is, we're applying a non-linearity, sorry, 10H to the cell state, and then dot product of that with the output gate. It'll sort of make sense in a second. I think this is a more visual representation of all of these gates. I mean, I'm not too familiar with like the logic gates and stuff, but this kind of makes sense. So it's like we have these inputs, then obviously we are applying these sigmoid functions. So I'll just go back. Yeah, you have all of the gate values are between 0 and 1. We are applying these sigmoid functions to all these individual gates. So that's why you see these individual gates. ft this is the forget gate. it, this is the input gate which goes into our particular, for new cell content, and it, we have this gate, and we are going to create this cell state equation, the ct. From that, so it's basically using input gate, cell state, and the sum of that with oh, not cell state, sorry, the new cell content, which is the c, and there's a tilde at the top. So input gate, new cell content, and previous cell content. So you are basically adding that. There's also a forget gate. So why is, oh yeah, forget gate is here, sorry. So forget gate multiplied by the previous cell information plus yeah, the product of these two. So that's what they create ct. It's a visual representation. I think you can similarly make sense out of that, but the idea is to make it easier to preserve information. By contrast, it is harder for vanilla RNN to learn a recurrent weight matrix that preserves info in the hidden state. Okay, now LSTM doesn't guarantee, obviously, but it provides an easier way for the model to learn long distance dependencies. It's just a caveat. LSTMs were the best in 2013, 2015. Now they're no longer. So no longer the dominant approach. Transformers are. So I think that just shows how quickly things just get evolved and moved on to a new version if something better comes out. The other one, to GRU, is I think it's a little more efficient, but the concept is pretty much the same. Instead of like 3 different gates, we just have 2 update gate and reset gate, and then we still have the same new cell content. We have a hidden state, which is basically sort of like a function of cell state and of cell state and hidden state in the previous version. So this sort of just simplifies LSTMs a little bit. So I would say computationally efficient, but I don't know from a performance perspective how well these would do. LSTM is a good default choice if your data is particularly long dependencies, but you can switch to GRUs for speed and fewer parameters. Yeah, here we are just trying to say vanishing gradients is not just an RNN specific problem. I mean, this is just a problem in general wherever you have some deep layers and you're trying to pass back the gradients. I think there were different ways around this. One of that is just to add the identity function. So you have fx and then just you add the x that preserves all of this, the initial information, the identity function, and then you basically pass that through ReLU function. So that's just a way to keep in mind. There are different ways to do that. Yeah, for example, densenet, highwaynet. I mean, these are different terminologies. I didn't see any value in just remembering all of these, just knowing that these exists to try to solve the vanishing gradient problems. So yeah, now I think the concept is bidirectional RNN, which we were initially just moving in one direction. We can do the other way around as well. Looks super complicated, but just the forward RNN, the red ones are moving right, the green ones are moving left. So we just have a better contextual representation from both left and right. So forward RNNs pointed right, Backward RNNs pointed left. Thing to note, ht minus 1 because previous word, t plus 1, the next word sequentially is actually the previous word here, so keeping that in mind, and then we basically concatenate these two. So this is the simplified, we just have arrowheads in both directions. Thing to note, bidirectional RNNs are only applicable if you have access to the entire input sequence. So language modeling, we can't use that because in language model we're trying to predict the next word, so we don't know that. This is important. I think later on we'll get to learn about BERT. I'm very excited to learn about this. Just a quick note, like BERT is bidirectional, so I think they're just trying to say how important directionality becomes. Multilayer RNN, I mean, just basically now stacking a few on top of each other. I think they're very deeper layers that exist in practice. But yeah, LSTMs are powerful, but GREs are faster. We need to clip our gradients in order to not just run away from our local minima. Use bidirectionality when possible because they are better performers. Multi-layer RNNs are powerful, but you might need skip connections or dense connections if it's deep, because it will keep on losing information as the further away we go. And then that was like a good summary slide to end this lecture as well. Yeah, let's just. Oh, we have a demo. Huh. Deep learning book. I think this is one of the books that was also mentioned in the class. Ian Goodfellow and these guys. So you can look at these if you want to just learn through the theory part. Yeah, archive. Nope. Okay. Oh, there's a code here. Didn't know that. Yeah, let's get back to this later if we get some time. Understanding LSTM networks. Oh, there's a blog post on that. But this is from 2015, so but at least this will give you a good understanding of what LSTMs are if you want to read through. Yeah, we're not looking at this. I think this code is a good visual representation. I think that's what it feels like. So we can go through this quickly if we can. Yeah, we're just loading basic stuff. Matplotlib. Generate some random data. Not linearly separable. Okay. I think this is what the data was. Interesting. Oh, so the sigmoid function, I think we're applying sigmoid function. Now I don't know how that is applied, so I'm just trying to figure that out. Okay. The sigmoid function squashes inputs to lie between 0 and 1. Yep, that's what's happening. Unfortunately, this means that for inputs with sigmoid output close to 0, 1, the gradient with respect to those inputs are close to 0. This leads to the phenomenon of vanishing gradients, where gradients drop close to zero, uh, and the net does not learn well. On the other hand, the ReLU function will not saturate. Okay, so defining, sigmoid. Oh, so this is just the input. So let's see how this becomes once these are passed through sigmoid and ReLU, for example. Let's try and see how these two kind of non-linearities change our deep neural networking practice. Below we build a very simple neural net with 3 layers, 2 hidden layers, for which you can swap out ReLU, sigmoid. Okay, so I think this is a definition for 3-layer neural network. Defining. Okay, so if non-linearity is ReLU, then if it's sigmoid, I think we can parameterize this for later, so that is great. I'm not going to model definition, but this is more to understand the concept. First, sigmoid, we have all of these iterations. So how to train with ReLU. Training accuracy was 97, great. Iteration 50,000, 49,000. With ReLU, training accuracy is a lot better. I mean, there's not a lot of difference between 0.97 and 0.99, but I think it becomes a whole lot of different once we are very close to like 100%. So the vanishing gradient issue. This is the sigmoid first layer, the blue one, and the green one is sigmoid second layer. Okay. Similarly for ReLU, sum of magnitudes of gradient, so it's like a strictly decreasing. No, not really strictly, but yeah, more or less. Interesting. Now this is for, we are basically plotting the sigmoid one. It's all squashed down. And ReLU looks a whole lot same. Okay, I think just because it was a simple example, there's not a lot of difference in what's going on, but that's why I saw not 0.97 and 0.99. But I think this is more to give a visual way of representing of what happens. But okay, we keep going to machine translation, sequence to sequence, and attention. Okay, here we go. Okay. Introduce a new task, machine translation. Introduce a new neural architecture, sequence to sequence, and then neural technique, attention. That's all we'll do. Section 1, machine translation. Simple translating sentence A from sentence X. Translating sentence X to Y. We are not going to history and stuff. I mean, it's just basically we want to find the best English sentence Y given the French sentence X. So it's basically condition probability. We're trying to do the opposite. One is a product of the translation, the other one is the language model. It's just a thing to know. One good point here, Rosetta Stone, I think, was like the same text is written in 3 different languages. So we have parallel data, which is very important if you want to do translations. Yeah. Now the problem becomes if it's not just a word level, if they're like phrases to phrases, so that becomes a problem. But the alignment is basically what word appears where. So if it's a simple 1 1 1 1, it's great. Japan is Japan, shaken is, yeah, so far so forth. But there's no equivalent for like le. We in English we don't say like the Japan. Literally we just say Japan, but Japan in French is le Japon. So uh, that's like the difference in the languages. So you don't see anything corresponding to le here. But yeah, now it can be many to one. I think it's a good representation. One to many, many to many. So yeah, fertile words are the words that have different. They're like one word has so many different words. Uh, so on Tarte basically hit me with a pie. I mean, I don't know if it's French language has this word that has like one word. I mean, a phrase specifically for hit me with a pie, but English has no equivalent word for that. And yeah, it's so many to many example. Uh, Property particular was aligning, particular fertility. Yep. Okay. So decoding for SMT. It's basically 3 steps. We're trying to find the argmax. We have to find the translation model and the language model. And I think some ways of what they were done in the past. But just to understand what machine translation is, it's a task given to the machine in order to translate from one language to the other. Now we'll do this via neural networks. So the neural network architecture is known as sequence to sequence or seq to seq, which involves 2 RNNs. So basically we have an encoder RNN and we have a decoder RNN. Is there more? Yeah, okay. So encoder RNN produces an encoding of the source sentence. So this is the French sentence. I'll go back to that pie hitting example. Yeah, so this is the sentence, and we're trying to get to this hit me with a pie translation of the French sentence. So encoding of the source sentence provide initial hidden state for the decoder RNN. So we come to this state, the end of the encoder becomes the source. This goes to the start of the statement. We apply argmax, and this is where he, and so on and so forth. We keep on going until the end. The target sentence is he hit me with a pie. So decoder RNN is a language model that generates the target sentence conditioned on the encoding. This diagram shows test time behavior. Decoder is fed in. Yeah. So the next input, and then we keep on getting the word or the target word which is required. Seek to seek is versatile. They more in machine translation. Yeah, similarly, some interesting ideas that I'm definitely eager to learn about. NMT seek to seek model is an example of conditional language model. So yeah, I mean it's basically we are finding the probability of next target word given the target word so far, and obviously the source sentence. So we keep on, yeah, if we backtrack that way, it becomes a conditional language model. How do we train? I think it's the same deal. We have the encoder, we have the decoder part. We calculated the cross entropy. We can go back, sending back the gradients for back propagation, and the average of all of the cross entropies is the system's loss. Seek to seek is optimized as a single system, and back propagation operates end to end. I think the idea of end to end was that it will go all the way back, if I'm not wrong, not just the first or the last word or anything. It'll go all the way back to the first word of the source sentence. I'll just check my notes if I have anything else. Yeah, okay. Greedy decoding. Okay. We saw how to generate or decode the target sentence by taking the argmax. But the fact that we are trying to calculate the probability of the most probable word on each step is a problem, because it might be the most probable for that particular place in the statement, but that doesn't mean it's the most probable for that sentence as a whole. I think the next slide gives you more. Oh yeah. So if we and also just keep in mind we're moving one word at a time. So let's say for this same French example, he hit me with a pie. After the word hit, we get as the most probable word that should appear after he hit or after he hit, but that's not the correct translation word, and we can't, there's no way to go back. So this is like greedy decoding. We are being greedy to find the best probability word for that particular spot. Instead of being greedy, we do an exhaustive search. Basically, we try to calculate the probability around all possible sequences of a particular spot, but obviously, you know, this becomes far too complex and expensive on a computation perspective. So I think that's where the concept of beam search becomes. We instead of all possible, we just do a top n, a k here. K is the beam size. We're trying to find the score for like the k most probable partial translations, which are also known as hypotheses, just a terminology. Thing to note, scores are negative, so the higher score is the better. We search for high scoring hypotheses, tracking top k on each step. Again, not guaranteed to find the optimal solution, but much more efficient than exhaustive search computationally. Just an example, if k is 2, we start off, we find that both I and he are the top 2 probable ones. Because we need to, we keep on moving, find 2 for each branch, then we select the top 2. So whatever, yeah, as I said, thing to note, scores are negative, so we want the higher score. So obviously minus 0.16, minus 1.7 are the top ones. So we basically drop struck and got. Keep on doing this for the top 2 ones. Keep moving. Yeah, I mean, obviously, finally, we're at the end of the statement, so we backtrack to see what the entire phrase was. Beam search decoding, stopping criterion. Sorry about that. It's cold here in Chicago. It's negative 5 degrees Celsius outside because of the wind chill. Okay, in beam search, because we may have different lengths of statements, we basically place a statement aside if it has reached end, and we keep on we continue exploring other hypotheses until all of them are complete. We can also define a stop condition based upon time or however n number of completed hypotheses. So it's all on us for how we want to define our beam search. just quickly be shameless about this. Yes, please subscribe. Thank you. Okay, finishing up, we've listed longer hypotheses have lower scores. Yep, that's the problem, because as you said, these are the probabilities are like additive. We'll keep on having a lower and lower. Just as an example, because this is a sum of the previous ones as well, we'll keep on have lower probabilities. So this is obviously a little unfair. So we normalize that by the length. Basically divide that by the length, so as to compare between different sizes. Advantages of neural machine translation over statistic. Obviously, this is a lot better stuff. Disadvantages, difficult to interpret. I think that's interpretability is a difficulty all across the board, or I think neural tasks, and difficult to control. So we may have safety concerns. What if a translation does something that we don't want in any real life context? Evaluation, BLUE is a methodology, bilingual evaluation under study. So I think they just said you'll see BLUE in assignment 4. I think it's just to keep in mind. Computes a similarity score, just to show how important neural machine translation has been, the progress, but we'll skip over this. They say it's the biggest success story of NLP deep learning. 2016 Google Translate switched from stochastic to neural. Many difficulties remain. I think these are ideas for you if you want to look at something and try and think on any problems to solve. But there are some issues, obviously. There are biases. There are issues around languages where we have very less corpus. So there have been so many improvements, and one improvement has created a new vanilla of sorts, one default, which is attention. That's what we're now talking about. So we've seen this. The problem with this architecture is that everything is dependent on the final word. Now this becomes an information bottleneck, because the context of all the previous words is also now dependent on this final word, because that is the input for a decoder RNN. Attention provides a solution to that. On each step of the decoder, we use direct connection to the encoder to focus on a particular part of the source sequence. So diagrammatically, we're taking a dot product of our start decoder RNN state with the encoder's first words state to calculate like an attention score. We do that for individually all words. With that, we softmax to get probabilities, and then we do a weighted sum to get to an output, which is the attention output, and that becomes or we concatenate that attention output with the decoder hidden state, because that becomes like the or that gives us a much better result. Now that we have a lot better understanding of the input statement as a whole. Sometimes we take the attention output from the previous step and also feed it into the decoder. So I mean, I think you get the point of we're trying to get the softmax around the attention scores, which are calculated by taking the dot product. From an equation, we have the hidden states. Then we have, let's say, for every time step t, we have a decoder hidden state. We're taking the dot product with all of the hidden states. That's why I get the attention score, which is ET. We calculate softmax, which is alpha. We're taking the weighted sum, AT. So softmax or whatever the probability distribution was. In this example, the probability distribution is now calculated with the weighted sum to the output, which is AT, and then we concatenate AT to the decoder hidden state, which is ST earlier on, and then we proceed for our words. This significantly improves NMT's performance. It solves a bottleneck problem, solves a vanishing gradient problem. It provides some interpretability. By inspecting attention distribution, we can see what the decoder was focusing on. So we get a little bit of an interpretation understanding. We get soft alignment for free. This is cool because we never explicitly train an alignment system. The network just learned alignment by itself. Now, attention is a general deep learning technique. We've seen that attention is a great way to improve sequence to sequence models. However, you can just use attentions in many architectures, not just seek to seek. There's several attention variants. So yeah, instead of basic dot product, we do multiplicative or additive. Yeah, these are just variants. In summary, we studied neural MT, seek to seek, attention. That's it. I'll see if I have something in my notes apart from this. Nope, that's it. Now this is the state of the art in the industry, so obviously super important to understand what goes on here. Sorry, I don't know why I click on that. Okay, I think these are mostly just notes and stuff. So we have statistical machine translation slides from like 2015, I think. But yeah, if for your reference, if you want to read through this, statistical machine translation. Blue, this is the evaluation methodology for machine translation. A paper on that. Seek to seek with neural networks. Google, 2014. Sequence transduction with RNN. Okay, 2012. Yeah, more papers. I think another blog for attention and augmented RNN. This is already 2016, so it's not like super new, but I don't know when attention is all you need paper came out, but I think that's like the paper I want to read. Massive exploration of NLP architectures. Okay. So yeah, I mean there are a lot of suggested readings if you want to read through these, but more important is just the concept around what is happening in this structure, and why is this important to use this over, or what does it improve over our previous vanilla seek to seek problems. So I think with that we're done for today. Let me know if you have any feedback, any questions. Happy to reach, if you want to reach out to me, happy to engage in any form, or in any social media. I have my link tree in the description, so all of my social media links are down there. Feel free to reach out in any platform that you're comfortable with. My plan is to keep on doing these daily, or maybe take a break once in a while, but as much as I can daily, with even my regular schedule starting in a few days. So I'll try to see how well I'm able to stick with this, but the idea is to keep on learning something every day, which is what I want to achieve. Right now I just have a few applications of NLP in my mind, which is why I'm trying to ramp up on this and get better as much as I can on the application part as well. I know we are missing out on a little bit of an application, but maybe we can, instead of one lecture day, we can just look at a few examples and try to just code uh, ourselves. The other thing, I mean, I feel obviously from this lecture, I'm trying to get my head around the concepts and definition and understanding of what goes on in the background. um, Obviously the coding part is also super important, but uh, I think that comes later once you know what's going on uh, in the background. Now uh, with that, I don't think I have anything else. um, Subscribe to my channel, hit the bell icon so that you are aware of, I mean, I do this every morning, um, 6:30 a.m. Chicago time, uh, I think 6 p.m. India time if you're from India. uh, but this is more of a discipline in this discipline in making rather than more about rather than the learning itself. Sorry, I can't speak. uh, but I think, yeah, that's it. I'll take my leave. See you guys tomorrow. Tomorrow we'll be doing lecture number 9. I think it's on, let me check. Practical tips for projects. Okay. I don't know how important this will be, but we'll still look through these because I think practical tips will give you, maybe, I mean, this is good to get an idea from a modeling or coding perspective. So yeah, we'll look at that as well. Okay, but with that, I'm saying this probably the third time, I'll take my leave um, and end this video. Thank you so much for watching, and I'll see you in the next one. Bye.